Chú vào lại cái link đi chú.
Hello. 1, 2, 3, my take. 1, 2, 3, my take. Vào là cái link á.
Từ từ. Nó sẽ hơi bị delay một tí. Ok, được rồi. Ok. Ok, được rồi. Cái máy này là được kết nối đi đâu ạ? Em vào rồi đấy. Vào rồi đấy. Vâng, đang chờ rồi. Quay chú à? Thế là nó ở vị trí này luôn? Thế để cái này luôn? Một cái là cam như thế, một cái là cam như này. Được không? Nhưng mà bây giờ không vào được à? Cho ai? Setup 2 vị trí con máy. Đấy, rồi. YouTube là được rồi đấy ạ. Thấy chưa? Check lại slide một lần chưa? Đấy, không biết là con cơ hội này hơi gần. Ở đây phải hơn nửa mặt. Để lên trên này. Lên trên này.
Livestream không mà Euro à?
Không, em live bằng mặt của chú. Mất rồi. Em thủ. Em người mở cửa. Em qua cái đấy này. Phải luôn ạ.
Phải tắt mic của cái này kia. Tắt mic của cái này chơi. Của cái đó. Vô lại đi.
Cái này đã vào được đâu?
Nhưng mà lúc vào là mình được.
Hình như cái này là mute.
Hello.
Hello em. À đây. Cuối buổi nhá. Nghĩa ơi, có gì em check hộ chị tí nữa nhá.
Biết chụp mát không? Biết chụp mát không?
Không sao đâu, chị nghĩ là nó không có gì đâu. Tí nữa ý là cái lúc mà vào cái này thì em chỉ cần mute nó đi là được. Em chỉ cần tắt
tiếng.
tắt tiếng ấy, tắt mic. Loa chị tắt rồi nhá. Em chỉ cần tắt tiếng.
Khi mà
Mình tắt mic ở đây đi, tại vì chỉ dùng một mic ở dưới kia thôi.
Ông nói là nó vọng đi vọng lại.
Đấy.
nghe tí nữa đấy được việc thì mình tắt được.
Đúng rồi, tại vì bây giờ thì chưa ấy. Xong rồi em xoay cái máy này như này. Em chỉnh để cho cái máy này nhìn thấy cái kia là được ấy. Xong rồi giảm độ sáng đi. Giảm độ sáng của máy đi. Giảm độ sáng hình như là ở đây này. Đấy, em giảm hết độ sáng đi để cho nó máy như cái máy chị này. Gặp lại em sau.
Vâng. Thôi,
Ừ,
anh nên kiểm tra xem đã được.
vào chứ, duyệt vào.
Không, ý là em tại mấy cái kia em thấy là mình chỉnh trước được ở đây, ví dụ như cam này anh thấy là ổn được.
Ok, con thấy chắc ổn rồi. Từ
Với cả
từ ngồi đây. Thấy đâu anh?
có
Chắc cho nó lên.
đây à?
Đây. Đấy người em.
Với cả em cũng chỉnh cho nó tự động roi thì tự động tắt mic rồi.
Tắt mic.
Thấy người ạ?
Thấy người.
Vâng.
Thấy đó.
Thấy từ đầu gối đổ lên.
Ok, thế là ok. Ổn đúng không? Ok. Lát thì ok, cảm ơn. Lát thì đến chiều đến ăn có ăn được không? 4 giờ không được à? Ok. Ừ. Mai như gì đấy? Mai như gì đấy?
Mai em đi Grab. Em đang ôn theo kiểu là học các cái thuật toán này, hay gọi là bảo tìm mắt tìm phân tích câu hỏi tìm được câu hỏi đấy nó còn khoảng là chứng minh
Ăn mà đấy không cái được mà ăn cái thuốc lát ôn ổn rồi thì thế thầy là dễ hiểu đấy. Có tờ là mình phải gửi quyền cho người ta trước để người ta đọc. Còn dân nhận tờ thì sẽ bắt đầu từ hôm nay đến đánh giá. Mình nghĩ không đúng đấy tiêu được thì ổn định được lát thì đây là
em nghĩ là cũng ổn rồi, cần thao tác gì thêm.
Ok, tức là chú setup để vào
Vâng, setup trong setting ạ.
đâu? Em không biết trục mát đâu.
Cho sáng. Đấy ạ, cái ấn
Test.
test ạ. Vâng. Đấy thì anh kéo xuống dưới, em có để là mute when joining.
Ok.
Video thì em chỉnh góc xem.
Ok, nice. Thế được rồi thôi.
Đấy ạ.
Ok.
Peut-être aller mettre les lumières.
Here. Slap.
The other one is something like that. Ah, yes. So you have someone online?
Yes. So I live streamed so my parents can watch from Vietnam.
Ah, but you don't have your the jury online. It's just for your parents.
Yes, one is for the jury online. I will use it.
Ah, so there is okay. So you have one jury online.
No, and for
So who do you have?
is it too brown?
Ah, Alain is invited.
Yes, but I don't like to bribe for the
Perhaps.
that this line.
You want to, but we will not see you well. If I turn off. Perhaps I turn
Spotlight.
one lamp. Can you turn off this one? That way you can still see yourself.
But the light they are
It's
not
the same.
directly into this light.
But, yeah, we need those lights to be turned off.
Yes.
This one? Yes, this one.
Yeah, much better.
Ah, Samuel. Sonia Vanier, it was one of my rapporteurs.
Okay. How was she?
During the defense, it's okay. But the rapport she did of my thesis is not really good. She wrote that there is 4 chapters, but there is only 3. So I don't know where the first one is going. So there's a bit of misunderstanding there. And Samuel Bertin was one of the 2 people that were in my committee of study. You know which year you have to do a CSE for your thesis, you have to tell in front of people. So it was one of them. Tu as connecté à Zoom?
Non. J'attends le host à commencer.
On peut se mettre sur le dos.
Ouais, on va peut-être se mettre sur le dos.
Ouais.
Moi qui espérais voir Sophie, les deux, Sophie et Sophie. Sophie, je savais qu'elle était dans le jury, j'étais dans son jury d'HDR et de thèse.
Ah bon?
Soit.
Peut-être ça. Ça, tout le monde peut vous voir.
Là?
Ouais.
Ok, ça
Au premier rang. Ça, tout le monde.
Je pense que je serais mieux pour le faire.
Vaut mieux pas parce que c'est et vraiment les juristes.
Ah ok.
Il faut un peu
On en fait, voilà.
Les vrais jeux.
Ah, on est que 4. Oui.
Nous on est là. Parce qu'il est présent. Tu sais, c'est comme les profs qui engueulent. Quand ils absent.
Ah oui, il faut qu'ils se défendent un peu. Non, rien.
Eh ben oui, ça va. Alors, c'est que, en fait, j'ai essayé l'été dernier de faire une couleur, et ça ne m'allait pas vraiment. Sauf que maintenant, ils sont décolorés, mes cheveux. Donc là, on a
Ça va plus leur
voilà, ils ne reprendront pas la couleur, il faut attendre que ça pousse et je vais récupérer.
C'est
Maintenant,
la
c'est javelisé, c'est. Voilà.
C'est la dernière fois que tu fais ça.
C'est là, exactement. Bon, j'ai essayé, non, je suis pas
je pense ça.
Voilà, c'est ça.
Mais tu peux pas remettre une autre couleur?
Si, mais c'est temporaire. Donc là, j'en ai fait déjà 2 fois, mais ça tient 1 mois. Et là, j'ai pas eu de
Quand
place.
tu fais une couleur, ça enlève la couleur du dessous.
Pour faire j'ai fait une couleur violette, pétard. Et donc, pour que ça tienne, il faut javeliser, il faut blanchir les cheveux.
Ah, par contre, tu pourrais faire une couleur qui javelise pas.
Pas mal de
Mais il y a
gens
des
qui
couleurs
font
que j'avais
des
pas.
mèches blanches.
Et voilà, donc il y a certaines couleurs.
Ouais,
pour
c'est ce que tu as fait.
J'essaie de parler.
Moi, c'est pas
J'essaie de parler si.
Alors,
Demander à reprendre
donc, non, mais ça y est, là, je suis en vacances, plus ou moins, puisque j'ai terminé mon dossier de demande de qualif. Ça y est, je l'ai envoyé.
La lettre que vous avez?
Oui, très bien, merci beaucoup d'ailleurs. J'étais très content.
Et vers nous quand même, parce que parfois je
Bien
fais
sûr.
des fautes d'orthographe.
Oui,
on
j'ai
les
revu,
capte
mais
pas, les noms de
Il va arriver de planter dans la.
Est-ce que tu. Charles, est-ce que. Elle était des réunions?
Oui, parce que je pense utiliser des formations.
Ah oui.
Donc, j'en prie. Oui, la caméra, c'est bizarre.
Oui, oui. Non, là, ça aide.
Donc, il faut quand même mieux les relire. Mais elle est tout ça qui voulait venir rencontrer Sophie comme
Attends, enlève pas le micro.
Bonjour tout le monde, vous m'entendez?
Oui, bonjour. Nous vous entendons.
Très bien. Moi aussi, je vous entends très bien, je vous vois aussi.
Bonjour tout le monde.
Bonjour Sophie.
Et bonjour à tous, salut Seigneur.
Salut. Bonjour à tous.
Bonjour. Merci beaucoup pour votre présence.
Et donc, monsieur Duano, il est là.
Oui.
Voilà.
Ah oui.
Je fais quelques commentaires sur le dossier. De toute façon, il était déjà bien avancé. Comme je te
Oui,
disais,
voilà, que je n'ai pas vu. Vous me l'avez envoyé?
je te le fais suivre, bon, Vincent et moi, vous avez déjà réagi.
Je vois qu'il y a Alain dans la salle.
Oui.
Bonjour Alain, comment vas-tu?
Bonjour. Ben, ça va très bien. Comme les vieux piratons.
Ben non.
Ah, si, un peu. Vous avez finalisé le dossier? Les deux points essentiels, alors, il y a ces découvertes. C'est ça. Ok. Et c'est quand même un sujet qui ne donne pas l'impression que il faut partager une boîte à faire.
Là, non, mais là, il n'y a pas de souci.
Je crois qu'il y a quand même une thématique généralisée.
Moi, c'est le sentiment que j'ai. Tu peux jeter un œil si t'as le temps. Si tu vois un truc qui te choque.
On va pas vous sentir. En bloc, il faut que Dominique, j'ai l'impression que c'est un projet.
Non, là, c'est. De toute façon, il faut aussi de ça. Il faut qu'on se mette d'accord. On va transférer ce standard du CNRS.
Et ça, la lutte, ça se fait sur plus tard. D'abord, c'est comme ça.
Oui, moi, je préfère qu'on
Au-delà du temps,
par exemple, professionnalise. C'est ce genre de trucs qu'il faut. Non,
Est-ce que tu peux décaler d'une place parce que on te voit sur
là, on a dit 25 ans. On est d'accord sur 15 points. C'est clair. On a une session après. Tu fais du boulot, tu remplis des trucs. C'est à la fin, ça commence.
après, ça peut se faire.
Oui, au moins, tu sais.
Oui,
Non, je suis d'accord.
non,
Mais
mais
si à la fin, ils proposent ça.
Oui,
Enfin, ici,
c'est assez standardisé.
Non, c'est pas très
Autour de 10.
Alors, le scénario, c'est 25 par an.
C'est intéressant en relation avec les relations industrielles, c'est pas très bien.
C'est pour ça que j'aurais transféré quelqu'un.
Pour ceux que les relations industrielles, c'est ça tout seul, c'est pas leur clé.
L'avantage, c'est que je suis très apprécié.
Il y a d'autres choses. Ça, c'est bien.
Bien. Bonjour à tous. J'ai l'honneur d'avoir été désigné comme président de ce jury de soutenance. Donc, Monsieur Chitao Nguyen, vous allez présenter votre travail intitulé The Pick Up the Delivery Problem with Compatible Robots. Donc, votre éminent jury sera composé de Sonia Vallée, qui est professeure à l'école polytechnique, de Samuel Berkhaen, maître de conférence ingénieur à l'INSA Lyon. Ce sont les deux rapporteurs de ce travail de thèse. Le jury est composé aussi de Sophie Damassé, maître de conférence ingénieur à l'école des Mines de Paris, et de moi-même, professeur à l'INSA Lyon, en tant qu'examinateur. Et il y a aussi Alain Quillot, professeur à Moss. Vous avez été encadré par Yetung Nguyen, professeur au NIMOS à l'université de Clermont-Auvergne, Jean-Philippe Guéon, de la même chose. Et puis, on a un collègue qui est à Hanoï, donc Anne Sonta, j'espère que je ne me suis pas trompé, qui est principal lectureur à Hanoï Université. Donc, on vous laisse 45 minutes pour présenter votre travail, et après, on passera au jeu des questions-réponses, en commençant en premier lieu par les rapporteurs, les examinateurs, qui donnera en dernier lieu à la parole à la présentation. Je vous laisse faire votre présentation.
Good afternoon, everyone. I'm Shita Nguyen, and today I'm delighted and honored to be here to present my work, the pickup and delivery problem with cooperative robots. The work is carried out at NIMOS Université Clermont-Auvergne under the supervision of Professor Nguyen. Professor Jean-Philippe Gaillon and Dr. Anfenta. And I also would like to thank the member of jury for being here and on the video. Here is the outline of my talk. First, I will talk about the context and motivation behind our problem and our work. Next, I will formally define the pickup and delivery problem with cooperative robots. That's our work. Followed by that, I will present to myth formulation and to heuristic algorithm. And the talk is concluded with redistribute, neighborhood, and taboo shirt. And finally, we will make some conclusion and a future direction. As you may know, e-commerce has grown rapidly recently, and that put a lot of pressure into warehouses. Warehouse now require faster fulfillment, higher throughput. In the US, in 2018, the warehouses are now the most common commercial building in number of building as well as total square footage. And in the traditional warehouses, manual labor account for 50 to 70% of operating costs, and that naturally pushes company to push automation into the warehouses. So basically, we have AGV, which is automated guided vehicle, or AMR, which is automated mobile robot that they can improve intralogistics, but not normally they are less flexible and they often struggle with oversight or large items. That's why we need a more dedicated, flexible, scalable robot system. As I just said, a single robot, AMR or AGV, often have limited load size and perception. A recent advancement in robotic system is cooperative robots, where multiple robots can collaborate to do tasks that a single robot cannot handle alone. As you can see on the figure on the right, we have two cooperative robots collaborate to transport a very large item here. A more recent advancement in robotics is reconfigurable robot, where multiple modular robots can attach or detach to each other to fulfill certain tasks. You can see on the figure, we have a single robot. If the package is small, only one robot is enough. And if the package is larger, then two robots can be configured together to handle this package, and so on, for three robots, and even for four robots if the package is too large. For this type of robot system, they have multiple benefits compared to traditional robot. First is more versatility, is more robust, as well as fault tolerance, and moreover, the cost is often cheaper. For the inside warehouses, there are few areas in optimization are currently researched. First, we have the multi-agent pathfinding problem, where we have to find a path for robot on a grid bay maps. In this problem, we must take into account collision, so we have to plan a path for every robot that they don't collide to each other. So in this kind of problem, we have optimal method such as A-star or conflict-based search. More importantly, we have scalable heuristic, because to solve this problem, we often need to solve it in very large scales in warehouses, or like the heuristic such as enhanced configuration or PIPT. Another type of operation problem in warehouse is involving transporting cooperative is the fit sizing problem and load assignment problem for cooperative robot. In this problem, we have to transfer a load or items from one place to another. There is no routing in this problem. And we also have another kind of collaboration is human and robot collaborative together. For example, human can retrieve SKU and robot handle the transportation. So in this problem, most problems focus on routing, assume that every robot work alone. There is no collaboration at all. And there are very limited research on problem integrate collaboration, reconfiguration, and a system-wide optimization. That's why we want to research the pickup and delivery problem. Now I will formally define it. We have in this problem, we have a set of robots and a set of tasks. Every robot starts at the depot and also have to end the path at a depot. These two depots might be at the same place. Every task is characterized by the number, by the pickup location, by destination, and more importantly, the number of required robots simultaneously. So this is what makes our problem different to other routing problem. So, for example, if a task requires 5 robots, then 5 robots must come to the task at the pickup point, and then they have to process the task together to the destination. And the processing time of the task will also have the travel time between task I to task J, or from the destination of task I to the pickup point of task G. The objective of our problem is to assign tasks to a robot to tasks such that every task is executed, and we want to minimize the max span, which is the time every task are finished. In this version, we assume that we don't take into account collision, and the robot also can work for infinitely. They don't require any recharge. Okay, to get more intuition about the problem, let's consider the following example. On the left, we have the map of 2 robots and 3 tasks. We have 2 diagonal tasks, each require 1 robot, and the horizontal task require 2 robots. So the robot, they have to finish on this task and then they return to the depot. On the right is one solution. So we can see that the yellow robot can do to execute tasks on below here. The green robot can go to execute the diagonal task in the top, and after that they join at the pickup point of the horizontal task at the middle, because it does require 2 robots. And if there are a robot come early, then it has to wait another robot to come. So when 2 robots come here, they can start to process the task and then return to the depot together. The solution can also be described by a Gantt chart. Here we have it is a process of each robot. First, we have the robot 1. They have to do task 2 here, and the robot 2 come to do task 3. After the robot 1 finish task 2, it comes to do task 1. But because task 3 haven't finished doing task 3 yet, the first robot has to wait for a certain time, illustrated by the block with a diagonal line here. And then the 2 robots can process and do the task 1 together. Yeah, the starting time of task 1. But the 2 robots must be at the same time. And then the 2 robots return to the depot. Okay. The traveling salesman problem is a special case of our problem when there is only 1 robot and every task has its pickup point and destination at the same place. The processing time of every task is 0, and so the PDPCR problem is also NP-hard. So with our problemify, our goal is first to mathematically modeling the PDPCR, how PDPCR can be formalized exactly. And more importantly, we want to solve PDPCR on large scale. How can it be solved efficiently in large scale? It can involve heuristic or neighborhood, etc. In the literature, there are several problems that are similar to PDPCR. First, I will talk about, for example, the resource constraint process scheduling problem, but with transfer time. This is a variant of RCPSP, where we take into account transfer time between activities. So this problem is closely related to PDPCR, where every robot in PDPCR can consider as a resource unit, and the traveling time between tasks in PDPCR is the transfer time in RCPSP. This problem was first formalized by mid-formulation and SCS-based heuristic. The most dominant method to solve this kind of problem is meta-heuristic, such as genetic algorithm, double short, and hybrid heuristic. We also have some research on exact formulation by Liu and Tran, but this problem comes from industry, so most of their work are focused on solve on large scale. Even PDPCR can be seen as a sub-problem of RCPS-PDD. It still have some differences. In PDPCR, with the time is continuous, but in PDPCR, the formulation are often discretized the time, and the precedent constraint in RCPS-PDD are also not appear in PDPCR. So that make a lot of RCPS-PDD method cannot apply to PDPCR. Okay, in the following, I will present two myth formulation to solve the problem exactly. First, I will talk about the VRP-based formulation. The idea of the formulation is to expand one task that require multiple robots into multiple tasks that require one robot each. And as you can see on the figure here, in the original problem, we had two robots for the task at the middle, and when it is expanded, now the two robots are expanded to two tasks. As the time requires two robots, now expanded to two tasks, which require one robot each. And so because it's expanded, so they are every task in the problem now require only one robot. And of course, we have to synchronize the time between the tasks that are expanded from the same task. To understand this formulation, we need additional set. First, we have set of n prime is the set of all the expanded tasks. We have the set n sub I is the set of every expanded task whose expand from the task I. I is the original task here. We have two variable. Xij is a decision variable equal to 1 if a robot going from expanded task I to expanded task J. We also have variable Zi to determine the time robot start working on task I. And here is the formulation. First, we want to minimize the max span. the starting time of the depot, of the returning depot. We have the constraint to make sure that M robot leaves the starting depot and N robot return to the returning depot. We have to make sure that every expanded task will be visited exactly once. And we have a software implementation constraint. It implies that if there is robot come from task I to task J, then the starting time of task J must be greater or equal than the starting time of task I plus the traveling time from task I to task J plus the time of task I. And the most important constraint to ensure synchronization between every expanded task. So this constraint makes sure that if task I and J expanded from the task J prime, then the starting time will be equal. Okay. In this formulation, we are expanded task. In the next formulation, we have the idea of the next formulation is we don't have to expand task anymore, and we treat every robot as a flow unit. So we call this the flow-based formulation. To understand this formulation, we need additional task. Task n plus is the every, as I said, n plus is the set of every task, and the starting depot, and the set of n minus is the set of every task and the returning depot. In this problem, we have additional variable Fij, indicate the number of robot traveling the arc Ij go from. So this is to determine the number of robots go from number flow go from task I to task J. Okay, here is the formulation. Again, we still want to minimize the expense. We have the constraint to make sure that n flow go out and return to the depot. We have a flow conservation constraint. The number of flow come to every task I must equal to the number of flow leaving task I and equal to the number of robots required for that task. The starting time of every robot is 0, and again we still have software limitation constraint. And to make sure, and the relationship constraint between f and x. This constraint makes sure that if there is robot come from task I to task J, then Fij must greater or equal than 1, and 0 otherwise. To analyze these two formulations, we generate the small scale generated instances. So these are the small instances where we generate to evaluate the performance of the mid formulation. In the instance, the robots are chosen randomly in 1 to 2, and the tasks are in the range in the set 5, 10, and 15. For every pair of robot and task, we generate 4 random instances. The tasks are generated randomly as follows. First, the number required robot for every task is in the range of 1 to the robot, and the coordinate of pickup and delivery are generated randomly in range 0 to 500. The processing time is the Euclidean distance from the pickup to the destination, and finally we have the traveling time is equal to the Euclid distance from the destination of task I to the pickup point of task J. And here the result. And in every round, is the average of 4 instances. As we can see that we have 6 rounds and 25 equivalent to 25 instances here. Every round is average of 4 instances. So on every formulation, we calculate the CPU time. The node reported by simplex, the optimal gap also reported by simplex, So if the gap is 0, then the formulation find optimal solution. And finally, we have the relative mixed span denoted by C max R. So this relative mixed span are for comparison purpose only. So if the relative mixed span of VRP formulation is 100 and flow formulation is also 100, then these two formulations perform find similar solution. Okay, as you can see that for the small instances where n equal to 5 and n equal to 2, or n equal to 10 and n equal to 2, both formulations are performed similarly, but the VRP model are generally faster. And for larger instances, neither model reach optimality within the time limit, which is 2 hours. We also want to see the limit of the formulation by testing it on the large scale instances. We'll also adapt these instances to test our heuristic and meta-heuristic later on. So we try to find the most suitable data for us to adapt. First, the RCPSP set like a transfer time, and the RCPSP DT, the version with transfer time, the instance size are very limited, so we don't want to adapt it. Instead, we adapt when no pickup and delivery problem data set from Lee and Lim. This instance size vary from 100, 200, 300 to 400, and every task already includes the pickup and delivery coordinate. So to adapt it, we just need to add the processing time, which is calculated as the complete distance from the pickup to the destination, and we'll assign the required robot for each task randomly from 1 to 5. And here are the results when we tested it on this large instance. So as you may see, both formulation struggle hard. So for every problem side here, every group here, we tested on 10 instances, and every formulation reached the time limit, which is 2 hours. For the VRP-based formulation, the gap is 0.99, which means it cannot improve too much from the initial solution. As for the flow-based formulation, C+ cannot find feasible solution within 2 hours, and that is why we need another method to solve this problem in large scales. This brings us to the next section, the grid algorithm. So first, I will describe quickly our initial idea comes from the nearest neighbor algorithm in the traveling salesman problem. First, we start from any city and we mark the starting city as visited. Then we select the closest unvisited city as the next stop, and we also mark it as visited. And we keep doing that until every task are finished and the vehicle return to the starting point, starting city. So to adapt this idea to PDPCI, it has some challenge because in PDPCI, every task requires multiple robots. Not only that, the robot has to work simultaneously to complete the task. That's why we come up with the grid append algorithm to solve it. The idea is similar to the nearest neighbor algorithm. This is an iterative algorithm And at every iteration, we try to assign the best robot to the best task. For example, here I will illustrate it on a Gantt chart. So initially, we have 2 robots and they haven't done anything. In the next iteration, these already tasks are assigned to task 1. So this is the best task because if we assign any other task to any other robots, the span will be greater than this. And we keep doing this. In the next iteration, we can assign this task, the other task here to the robot 2. And finally, the brown task here requires 2 robots. And the robot 1, since it finished the task originally, it come here and it have to wait for a little bit before they can do the task together. Here's more detail of the algorithm. First, we start with every robot at the depot, and they pass content only the depot, and the path down is 0. The main iteration, we want to choose the best task. At every iteration, the best task is the task that has the I smallest value in increase of the max span after appending it. So if task 5, if task I require 3 robots, for example, but the max span that we have to compare the third smallest value of increased max span. So that is the comparison element between choosing the task I, which is the best task I at every iteration. And then we append the chosen task to the path of the robot, and we must synchronize the time of the chosen path to be the time of the I smallest increase in max span. For this algorithm, the results stay the same for no matter how much we run. So we come up with another idea to introduce some randomness into the greedy append. We call it the S-greedy append algorithm. In this version, in the input, we are given an insert range of K1 and K2. Again, we still on the robot start at the depot, and they start the same as the greedy append. But in the main iteration, at every iteration, we choose a random K such that K1 smaller or equal to K and smaller or equal to K2. And then we try to insert up to K, this K task. Why we have to try? Because, for example, we have only 5 robots and we want to insert 2 tasks, and the 2 tasks, the total number of robots required for these 2 tasks are 6, for example, is greater than 5, then we cannot insert on the 2 tasks, we just can insert the best task here. Again, we still append the chosen task to the path of the robots. And finally, we still have to synchronize the time of the chosen path. To evaluate this formulation, we want to compare it with simplex on large-scale instances. So, and in every round, we have 10 instances, and we run S-greedy fit times. As you can see here, both versions of the greedy algorithm outperform simplex by a large margin in both solution quality and solving time. For example, we set in the case of n equal to 200 and n equal to 10, we set the simplex, the PRP formulation as a baseline. So it has relative max span equal to 100, and for the greedy append version, it finds a solution that has relative Cmax equal to 20.2, which is around 10 times smaller in 5 times smaller in max span. It's also for SVD12, it also find much better solution compared to PRP formulations. So both of these formulations solve in just a few seconds because we run SVD 50 times, so it takes longer, 21 seconds compared to 1 second in Japan. Next, we also want to compare several versions of S3D compared to grid Japan. So S3D12, the insert grade is 1, 2. S3D13, the insert grade is 1 and 3. And also S3D23, the insert grade is 2 to 3. We can see that S3D outperform grid Japan in all instance sizes. And among the version of S3D, the S3D12 perform the most consistent here. So for grid Japan, the relative max span is 100, while for S3D122, the relative max span is 94.8 on average. Note that because we run the S3D for 50 times, so they take 20 to 40 times longer compared to grid Japan, but the solving time still small related to compared to the more advanced method. The purpose of the grid Japan or grid Japan is to construct an initial solution for more complex meta heuristic in the upcoming section. Now I will talk about our new redistribute neighborhood and double search algorithm. So the purpose of this neighborhood is to integrate it into multiple meta heuristic schema. First, to understand this, we have to know about the solution representation by a directed acyclic graph. Every solution in PDPCR could be described by a directed acyclic graph as follows. Every node represents a task. In this example here, we have 5 tasks, A, B, C, D, E. S is the starting depot and S prime is the returning depot. And every flow unit represents a robot. So on the figure, you can see from S to A requires 5 robots. So we have 5 robots come from S to A and 2 robots come from S to B. Task C requires 2 robots. We have 1 robot come from A to C, and we have 1 robot come from B to C. And here is the input information of the solution. We know that we already know the number required of every task, as well as the traveling time and the processing time. The traveling time represented by the purple number on the edge, and the processing time is represented by the purple number on every node. So, okay, now we'll explain the earliest starting time and the longest path to the sink in order to understand the redistribute neighborhood. For every task, we know or calculate the following. We know the processing time Cj is given in the instance. We can calculate the earliest starting time of every task J. And we also can calculate the earliest finishing time of task J, the blue number on every node here. It is equal to the earliest starting time plus the processing time of that task. For example, for task I here, the earliest finishing time is equal to traveling time from S to A, 4, plus 1 is the processing time of task A, so we have the earliest finishing time of task A is 5. Similarly, for the task B, the earliest starting time is 9, because it is equal to traveling time from S to B is 7, plus the processing time equal to D. To B is 2. But for task C, we have flow come from task A to task B, so this earliest finishing time of task A would be the maximum of earliest finishing time from task A plus the traveling time from A to C plus the processing time of task C. So from A to C, the possibly earliest finishing time is 5 plus 5 plus 4 is 14. But from B to C, the earliest finishing time is 9 plus 3 plus 4 is 16, because this is 16 is larger than 14, so the earliest finishing time of task G is 16, and etc. And we also can calculate the time of the longest path from any task to the sync. It's basically a reverse of the earliest finishing time of every task. So we can do it, but now we do it from S prime to backward to S. Next, I will explain about topological ordering. So a topological ordering of a directed acyclic graph is a linear ordering, such that for every arc ij in the graph, I is before j in the ordering. So on the figure here, we have S, B, A, C, E, S prime is the topological ordering of the previous shown graph. And to the redistribute, they would start by perform a cut on the topological ordering, and thus split the graph into two parts, left and right. Here on the ordering, we have a cut between C and D, and that's corresponding to this cut on the graph. On the left, we have S, A, B, C, and on the right, we have D, E, and S prime. Our objective here is to redistribute the flow between the cut and to minimize the max span of the solution. How do we do that? Okay, let's look at the following figure. On the left, we have the task on the left of the cut. On the right is the set on the right of the cut. We still have A454 here is the number of flow we can transfer between the cut, and one is task B can transfer one flow to the right, etc. We can observe that if we connect task I from left to task J from right, then the max span of the solution will be at least the earliest starting time of task I plus the traveling time from task I to task J plus the longest path to the sink of task J. And to solve it, to minimize this max span, then we can solve it by a mid formulation here. So we want to minimize the CMAP, and the CMAP is must be greater or equal like here. That's I bar plus Dij, the traveling time plus the Zj star is the longest path of task J to the sink. So this formulation can be solved by simplex, but we also propose a combinatorial algorithm to solve it more effectively. So the idea is we attempt to iteratively decrease the max span by removing the critical arc through a flow transfer sequence. I will explain the flow transfer sequence in a moment. And while we alter the flow value, we have to find new alternative successor and predecessor for the node on the sequence, and we stop when we can no longer improve the max span. Here is the example from previous graph. On the left, we have A, B, C, and on the right, we have B and E. Currently, from A to D, we have 4 flow. From E to E, we have 1 flow. And from C to E, we have 2 flow. Here, the critical arc is CE. Now we want to remove entirely the arc, the flows from C to E. So we do this we want to find alternative successor to C. So for example, with an alternative for C is D. So there might be an alternative successor for D, because from C there are new flow come from D. Then we have to reduce the number of flow that already came to D, which is from A. So that is, we have this line here. And finally, because we are reducing number coming from A to D, we have to find a new flows come from A to other node on the right. So that's why we have alternative successor for A is E here. And here we can redistribute flow after we reduce two flow from C to E. Now these two flow come to D, and also another, we reduce the number flow from A to D. Now we have only two flow come from A to D, and then we add two flow come from A to E. Now the critical arc is gone. The old critical arc is gone, and here is the final flow between the cut. So in the solution corresponding to this flow, the wingspan is decreased. Already decreased to 22. Previously is 25. Okay, so we want to evaluate our new neighborhood. So we integrate it into a Tabucha scheme. So here is the basic of Tabucha scheme. First, we find initial solution. We set it as the current and the best solution. We initialize an empty taboo list. A taboo list is basically a set of part of solution that we cannot accept a new solution. So if the solution is in the taboo list, then that solution is not accepted in the neighborhood finding steps. So we have an iteration. At every iteration, we generate candidates from neighborhood of the current solution. So our redistributed neighborhood is integrated into this step, and we evaluate non-taboo candidate. We set the best candidate as the current solution, and we then update the taboo list. Finally, we update the best solution if possible. It is better than the current solution. And we remove the oldest element from the taboo list. The taboo list have the limit sign. We initialize it. To evaluate our neighborhood, we integrate it into, we compare it with the state-of-the-art taboo in RCTS PTT paper. It has already two neighborhood, and we have made some adaptation, and then we apply it to the taboo. So the baseline is called TS2N, taboo to neighborhoods, and our method is TS3N, is neighborhood. But basically, it is the state-of-the-art method, but we want to keep the solving time competitively between two formulations, so we reduce the exploration of neighborhood of the two original neighborhood at every iteration. So here is the result of 40 instances for each round, with 10 instances for each and for exact in the size 100 to 400. So we can see that with the redistributed neighborhood, our method find better result on larger scale problem in shorter time. For example, with n equal to 10, our DS3N find better result in 32 out of 40 instances, with average mixspan of 92.9 and the average mixspan of 98.4. Similarly, with larger number of robot size, the average mixspan is 95.3 compared to 100 of DS2N. And here is the graph of decreased mixspan over every iteration In the x-axis, we have the iteration up to 5,000. In the y-axis is the best span relative to initial solution. So for the DS3N, our method is described by the blue line, and the original method is described by the orange line. So we can see that our method is much quicker in the initial solution and find better result. And so DS3N, our method requires under 500 to reach a solution quality that DS2N, the orange line here, achieve after 5,000 iterations. Okay, so to conclude this talk, in this presentation, I formulated the pickup and delivery problem with cooperative robot. I present two mid formulation and two heuristic approach that outperform the simplex formulation on large scale instances. I propose a normal neighborhood structure that can be applicable to a variant of the heuristic, and we choose W shirt to integrate it into, and it already outperformed the state of the art W shirt in ACPSP DT. But we still have some room for improvement in the future. First, we can enhance the redistribute neighborhood where we don't really need to cut and redistribute. Now we cut when we insert a task, and after that we redistribute the flows. It can be applied to partial solution as an insertion method, for example, to construct an initial solution, or to apply as a in adaptive in large neighborhood search. To make the problem closer to industry real life scenario, we can consider battery constraint, where robots have a limited travel distance and they have to visit charging station as needed. And after the charging, the robot can go to do the task normally. And we also want to consider a variant of PDPCR where we solve it on a grid ratio and we take into account the conflict between robot while traveling. Here are the list of conference proceeding and submitted paper. And that is the end of my presentation. Thank you so much.
Merci. Thank you for your presentation. Could you switch to remember? First, I propose to start with you, Sonia Vanier, the first rapporteur.
Okay, thank you. Thank you very much for this presentation. Very interesting problem. I think that there's still a lot of things to do. I have just a few questions to more understand what you did in your work. My first question is about the flow formulation, your mid flow formulation. I might come back to the formulation. Yeah, the mathematical problem. Yeah. Yes, this one. Yeah, so here you use a compact formulation, so flow on arcs, and you used just simplex, as you just introduced the model as it is on simplex and get an optimal solution. Am I right? Yes. So did you try, because you have to find path for the robot, so did you try the path formulation? Because with path formulation, you can use column generation, which is usually very efficient for networks optimization problems and on flow. Did you try the path formulation for this problem?
The path formulation, I'm not sure. I haven't tried. So basically, we just tried these two formulations, and our goal is to solve the problem on large scale instances. So we we haven't tried much more formulation for this problem.
Okay, because when you showed your numerical result, I think the need for a flow formulation was worse than the VRP formulation, but usually it's just a compact. Maybe it's just because it's a compact formulation, and if you try the path formulation with coordination, it might be better. I don't know what is your opinion on that, because you know your problem much more than me.
I'm not sure about path formulation you are talking about, because so I'm not sure what is path formulation in this case. So can you elaborate more?
Yeah, for flow problem or flow formulations, you have flow variable on arcs, which is the compact one, and you have flow variable on path. So you have the flow on a path, and usually we can solve the problem easily or efficiently with column generation. But maybe I missed something for your problem.
Okay, thank you. I can look that into the picture.
Yeah, they are very efficient. Column generation is very efficient, and you can get also a nice theoretical result with it. And also for compact formulation, we can solve them efficiently with the cutting plane algorithm. To speed up the solution problem. So instead of just putting your model in Cplex or Goruby, you can speed up the solution by using the mathematical properties of the model. Adding some valid inequalities which any integer solution should respect. And these approaches, I think Viet is really specialized on this kind of approach. So did you check or take a look on this approach for your problem?
We haven't tried it yet. So basically, like I said, we want to solve it in a large scale. So that's why we want to focus more on
Thinking about cat.
Hello, can you hear me?
Yeah, please go ahead. Yeah, please go ahead.
Okay, so basically, we want to focus more on trying to solve it on large scale problems, and so that's why we focus more on the heuristic and the beta heuristic size. So
yeah, it makes sense. It makes sense, but sometimes having the optimal solution with efficient tools may give good idea to speed up also the heuristics sometimes, and they're getting some good and interesting bound on the problem. Yeah, I have the same kind of questions on your slide 28 when you talk about cat on your graph. When I see that coming from the network optimization community, I think about the cat inequalities, for example, for your problem.
Slide 28.
Yeah.
Yeah.
Yeah, this one, for example. In this case, maybe you can add some valid inequalities or cat inequalities to improve solution and have also interesting theoretical result. But it is still on small size problems. But as I said, it might be interesting to get a good idea from the exact approach to improve the heuristics. And you have also all the problems in the literature in the last mile delivery problems. We have a very good team on that at the ESSEC, especially the work of Ivana Ljubic, Claudia Archetti. They have a lot of work on the VRP and last mile delivery problems. I don't know if you already take a look on their work and if there are some connections also, some relation with these.
I'm not sure, but so I searched a lot of literature, and the two types of problem that I found the most similar to now is the SPDD, which I explained earlier, and another type of problem is the vehicle routing problem with synchronization constraint. Both of these problems have very limited number of research. Like for its type problem, it only has like 10 or 15 papers of this. So I'm not sure if there are some other problems that are similar to ours, or we can take idea from some other problems.
Yeah, I think you can take a look on the work of Ivana Lubich, especially with bi-level optimization. And they have included also in their research work the uncertainty on problems. So like a robust bi-level optimization might be a good idea in their work.
Thank you.
And yeah, just another advice, because for the multi-agent path finding problem, there are very efficient and very interesting problems which really scales with the reinforcement learning. So combining the optimization approach with the reinforcement learning, and they really scale up to more than 1,000 number of robots. The graphs, I think it might be interesting also to take a look on the work coming from the learning research and the reinforcement learning. They have a very good numerical result on that with good solutions.
Okay, thank you.
Just last question. Do you have plan for the future?
Yes, I have some plan, but so I want to try to work in some industry, in logistics or robotics, for example. I want to research if I want to explore myself in this environment.
In France?
Yes, France.
Ah, okay.
Europe, yeah.
Okay, good. So thank you. That's it for me. Thank you very much.
Thank you.
Thank you, Sonia Badin. Samuel Lafay, you can start.
Hello, do you hear me?
Yes, very good.
So thank you for this presentation. I want to thank also the director for inviting me to this jury. Okay, so I also think, like Sonia, that this problem is interesting, and there are also a lot of perspectives. My first question is, where comes from this problem? Do you have an application from a dedicated industry, or is it a purely theoretical point of view?
So the idea comes from the industry scenario where we need multiple robots to do certain tasks inside warehouses, the pickup and delivery task. And like I said in the introduction, where packages are too large and cannot handle alone by one robot. So that's the idea come from the industry. But currently, this version we still need some more tinkering and, for example, add some constraint to make the problem closer to real life scenario. Okay. That's what we want to ask.
Okay. So my first question is about slide 10. You talk about the precedence constraints. That it's possible to add precedence constraint in the RCPSP, so of course, but is it possible to add precedence constraint like RCPSP in the continuous time model?
Yes, I think so, because we have this software elimination constraint is that if task I is must, so I will try to formalize the precedent constraint in continuous model. So if task I is the subsequent, is the precedent of task J, then the starting time of task J still must greater or equal to the starting time of task I plus the this constraint. But for
Okay, well, we all agree it's possible also to add this constraint in the VRP model. So I think it's not the main difference from the RCPSP. The main one is the only one maybe is the discrete time. Okay. Oh, on this, I think it's possible to reduce the number of constraints here because the line just after the blue one, the I, the J, I think it's possible to remove G prime here and just n number of constraints and dot n square, but it's just a very short point because I see this, but I didn't want to talk about that, but because it's displayed, I talk about it. Okay, on slide 23, you talk about the randomized construction, greedy construction. Can you go on slide 23, please? Okay, maybe here I didn't understand something, but when you choose a random K insert, do you choose the task or do you choose a number?
I will choose the number that I want to insert, the number of tasks I want to insert in that iteration.
Okay, so at this point, I didn't see the difference between this algorithm and the previous one because at the end you insert all the tasks.
No, but okay. In this attribute version, we can insert 2 tasks at the same iteration. But for these 2 tasks, the number of the 2 tasks, the number of robots required for 2 tasks much smaller than the number of the number of total robots. For example, if we have 2 tasks that require 6 robots total, but we only have 5 starting robots, then we cannot insert 2 tasks at the same time, at the same iteration.
Okay, I'm sorry, I don't understand. Here you choose a number of tasks. Where do you choose the number of robots?
We don't choose the number of robots, depend on the number of tasks, of the chosen task. So K insert here is to determine the number of tasks we want to insert and to append into the robot. Let me try to explain by the figure here. So in the initial version, at every iteration, we try to insert only 1 task. So that's why every iteration the increase. But if we want to insert 2 tasks, for example, if you want to insert, for example, the brown task and the orange task here, the brown task you want 2 robots and the orange task require only 1 robot, then the total number of tasks is 3, and we cannot append it into the robot path.
So it means that you prefer to insert tasks that need only 1 robot in this case, less robot than many.
No, I don't think that's the case. So we just want to insert the tasks that make span, increase the list. We have to do. I have to add that when we insert more than 1 task at every iteration, the robot must not overlap. So every robot can only do 1 task at that iteration.
Okay, no, I'm sorry, it's really not clear for me. In your manuscript, you say on algorithm. I'm a little bit lost in the manuscript. Okay, it's algorithm 5. It's S greedy.
Yes.
You say you choose a random number. Okay, then in other instance, you want to add a given quantity of tasks to the robot tasks. And here, in my opinion, I will give you my opinion. The random part is just the fact here that you cannot add, when you choose maybe to add 2 tasks, you cannot add these 2 tasks to the same route.
Yes.
It's the only part which is random here, but it's you decide to add a set of tasks to different routes.
Yes, that's correct.
Is it that?
Yeah.
Okay, because I asked this question in my report, and I asked the question again, and in first intention you are not able to answer this question, so I'm a little bit confused.
Okay. Yeah, I explained it a little bit back there.
Okay. So then maybe my last question, 30 in slide 34. Okay, here, in my opinion, the 5,000 iteration is not enough to observe that that converge. How many iteration is needed to get maybe the best value that can be obtained with this method?
So I think you can run for as long as you want. I'm not sure. Can you repeat your question? But in my experience, this iterative method often run from 5,000, 7,000, 10,000 steps, and then they stop.
Yeah, but here it's possible to make more iteration and observe better results. Do you think that for this instance you obtain 93% from the beginning? Is it possible to improve it?
Yes, I tried it.
Much more?
Yes, I've tried it in several instances. I run it up to 10,000 iteration, and as the iteration goes, the converge speed gets slower and the improvement getting smaller.
Sure, for sure it converges, but how many iterations is needed to have a pretty good convergence? But because here I don't think 5,000 is enough.
Okay. So if I say it could take around 15,000 iterations to be sure, but to be sure that the conversion is good enough. In the paper I read, we basically choose determine a number of iterations beforehand, and we cannot make sure that when the convert is good enough. So.
Okay, because in your documents on page 92, you present 2 graphics, and the second one is the one displayed on the board now, but the other one is definitely not converging. Okay, the gap between TS2N and TS3N is pretty much constant, and the evolution is nearly linear. It's not an exponential one, so we don't observe the converging in the figure 5.5a, page 85. So I also wrote this question in my report, and I hope to see another curve today, and I'm little bit confused about didn't see it. But, okay, it's done for me. I don't have other question. Thank you.
Thank you, Samuel. Sophie Damassé?
the presentation. I appreciated a lot. Really clear and just like your manuscript, it was really clear and nice to read. Thank you for that. Each time I read about this while I was reading your thesis and while I was hearing you talking about this problem, I oscillate between thinking it is a scaling problem or a routing problem, and yes, the fact is sometimes I would say, oh no, it's just a scaling problem because your robot that do not have to go back to the depot. Actually, you do not care when they go back to the depot, or you do not care about how many time they take to make their tour. And some other times I'm thinking it's a routing problem because, or at least it's not a cumulative scaling problem in the sense that your robot, there are not the resources, there are the unit of resources, and so they are differentiated, and so it's more an end machine problem than a LCPSP, and so it's really interesting to have these two aspects. And for you, what do you think? Is it a routing problem or a scaling problem? What are the more dominant aspects of this problem?
I think they are both. We also have to, like, it has routing element and it also has a scheduling element. As I read right in my manuscript, it can be an overlap between routing and scheduling. But if I have to choose, I will choose it as a routing problem.
But don't you think? Oh, sorry, you're not done.
Yeah.
Okay. For me, I see a warehouse as a small place, so I'm thinking that the robot they do not have a long travel to go from one task to another task, and on the contrary, you may think that they often have to synchronize these robots to get to get this heavy task, and so the duration of the task can be also increases there. So I think that in your instances, you take as the duration for the task. You took the Euclidean distance between the start and the end of the task, but actually we can think of a time for the robots to synchronize on this task and just to hold the object there to transfer, for example. So for me, the duration of the task, they can be much higher than the duration for going to one task to another. And in this case, could it be seen as a scheduling problem more? And in particular, my question is that you choose to take VRP instances to build your own instances. But what happens if you have taken an RCFPSP or at least scheduling instances, and if you have added this kind of setup times due to the transfer? This could it change the efficiency of your method if you have instances that are more scheduling than routing?
So because I haven't tried to adapt the instances from RCPSP or scheduling yet, so I can not tell for certain, but I'm pretty sure that the performance that will not have much changes in the performance between the two models. Is that what you mean?
Yeah, I think I think that it will change a lot. I don't know, but for example, when you look at the MILP results, you only tested on two. So for the generated instances, there were only two robots. So actually either your tasks are completely synchronized between all the robots, because there are only two, or the tasks are just for single robots. And I'm wondering if it would change a lot the results if you have perhaps less tasks, but more robots. And then you will have less synchronization to it will be less constrained your problem because you will have less synchronization to take into account. And so I'm wondering if the instances that you have, perhaps they are a bit limited to understand how the milk formulation could work on instances with less synchronization. But I do not know. It's just an intuition that it could have some impact on this. And what another question? Yes, you mean this problem is not the RCP SPTT, so with transit time. The RCPSP with transit time, because so it has precedence constraints in your model. So it is not the real difference, and the difference is the fact that you have discrete time. These are not discrete time models here, but in scheduling program we have discrete time model. Actually, this is not true, and you have a scheduling a real job shop problem or something like that. We do approximation when we discretize the time. So is it really a difference here? Do you really consider that your instances cannot be discretized?
Could you repeat your question, please?
Well, yeah. So the slide that you show here is the right one. The fact that as a difference from your problem to the RCP SPTT, you cite only two aspects. The first one is the fact that there are no precedence constraints. That, as Sandberg said, it is not really a real difference. And the other is the fact that RCP SPTT are considered discrete time. So there is a discretization of the reason. And you say that it is not the case for you, but actually it's only depends of the kind of instances, of the kind of durations that you consider in a real scheduling problem, in a real world scheduling problem. The time is not discretized at all. So what makes you think that your problem cannot be discretized?
Of course, I think that if we want, we can generate instance where every time is discretized, but we want to solve it in continuously. So is that what you mean?
The fact that your instances that you have generated, they are discrete. It seems that I think that you only took discrete durations and discrete. I know you took directly distance, but well, so for me it is not a clear difference between your problem and the RCPSP and the RCPSP-TT in particular, and so the fact that there are a lot of works on the RCPSP that work on discretization, time discretization. My question was, why do you you cannot use these results because you say that your problem is not discretized, and perhaps it could be also an option to look at solutions that are based on discrete time. But
I still don't follow. Sorry. So, what if I understand correctly, you mean that the PDP-CR can be discretized?
It seems that I do not see why it cannot be. for me, it can be discretized just like any real-world scaling problem is approximated as a discretized. The discretization is used to model the fact that you have distinct synchronization of resources, and so these are discrete aspects, and this discrete aspect, you need the discretization of the times to do that. And I'm wondering why in your problem, so you cannot use this modeling trick.
I haven't think about our problem to a way to describe our problem to discretize the time yet. So maybe that is a direction in the future.
Mm-hmm.
If you add the discrete time to the true model,
Okay.
will they be more complex than the model? Much more complex,
Mm-hmm.
or not?
So if with the time is discretized, then
You could, for example, use these time-indexed models, for example, in mathematical programming approaches. Or perhaps it gives you also another representation of your solution. So I just say that it opens other solution approach for your problem, and so it will be interesting for if you have applications to see whether really or not you can do this discretization or not. But I do not see how. For me, it is not. I do not see where there is an additional difficulty to do that, but I do not. I'm not sure at all. But okay, so let's. I just will ask a last question, if you don't mind. In the future rocks, you present some extension of your problem, and I think. There is one in particular that I appreciate. Oh, actually, I have two questions, but just this one. For example, when you talk about charging your robots, if you have electrical robots and you have to charge them, do you already know how you could handle this charging? Could it be consider as an additional task or something like that? Did you think about this problem in particular?
Yeah, I thought about it. So basically, every robot has a new battery limit associated with every robot, and we have to make sure that if a robot go from task I to the task J, then the remaining battery must be sufficient to do that task. Otherwise, the robot must return to must go to the charging station. I have that idea in mind, but I haven't concretized, haven't formalized it yet.
Okay, no. So this is a problem that you want to consider, but that you could consider, but you didn't think about how you could model this in your program, and how the approaches, the different approaches that you propose, they are robust to this kind of extension. So this. My last question is, so I think this your algorithm of flow redistribution, the combinatorial algorithm for flow redistribution, is very interesting. And so, for example, just this one, how robust this algorithm would be to this extension?
How can it, if I understand you correctly, you asking that how
Can
can
your algorithm to add? Sorry,
I can.
No, sorry. I just said if you added this constraints, the fact that your robots have to go charging and have limited time for traveling. How this extension, do you think, is it easy to integrate your combinatorial algorithm for flow redistribution?
Okay, I haven't think about it yet. So,
Okay.
so maybe, yeah, that is an interesting perspective. So,
Okay, so and just so my last question. So I appreciate a lot this part of your work, and in particular, can it be applied to RCPS PTT? This one in particular.
yes, I have an idea to apply the redistribute neighborhood to other problems like RCPS PTT. So
Okay.
basically, we have to ensure the precedent constraint when we
Yes.
do the flow redistribute between the count.
Okay.
Yeah.
Yes, you have the precedence constraint to take into account. Okay. So thank you very much, and thank you again for your
Thank you, Sophia. So I will change my job. I will ask questions. My first question is related to the application part of your work, because I do not understand if you think you are able to address real-size problem. Do you have an idea of how many tasks and how many automatic the mobile robots is possible to find in a real industrial case?
Yes, I've looked into several sources, Amazon,
Yes,
etc.
for example.
Yeah, so they still have, for example, every day, every robot do for like tens to hundreds of tasks, for example, but they doesn't require cooperative between robots. So
10,000?
no, 10 to 100, around 10 or several hundred tasks, for example.
Yes, okay. So you are the same size?
So my size currently is a little bit smaller than
Yes.
the real.
So in that case, what has to be done to be able to address the real size problem, in your opinion?
I think so. The question is how can we address the?
You say that you currently are not able to address real size problem. Yeah.
Yes.
Yes. What do you think? What has to be done to be able to address real size problem?
So I think these formulations are very capable of addressing this side problem, the heuristic and the redistributed neighborhood that we just after the spread is very capable of addressing this size. So currently I'm implementing the algorithm in Python.
Yeah.
So
okay.
Yes. So like if we need really high performance, we can implement it in C++ and C++ and Rust, for example. So
you really increase it.
I think the size is not really a problem to until it is too big.
Yeah. And the second question is related to an extension of your model. Currently, every task has to be done as early as possible.
Yes.
The next time. But is it possible to add, for example, a due date for each task? Because in a logistic warehouse, maybe some tasks have to be filled in the same truck and have the same due date. Is it possible to extend your work?
Yeah, I think so. So I think you are talking about time window.
Yeah, not exactly time window, but a due date for each task. It's close to time window, yes.
So we can need another constraint instead that the finishing time of every task will be smaller than the unit. That one.
And I have a question integrated, but I don't know the word in English. Because in the warehouse, you have different streets. Les allées, je sais pas comment on dit allées en anglais. Alley. Okay, so you have different alley, and in your case, you don't take into account the alley capacity. Is it possible to have 10 robots in the same time in the same alley?
So in our problem, we don't take collision into account. So
yes, not collision, but maybe you have smart robots. You have no collision, but they have to wait that a team of robots do their job. So the second job have to wait, for example. In my opinion, it's important to take this aspect into account. You have many robots in the warehouse. Do you think it's possible to address this aspect in your work?
I think what you mean is we solve on a grid, and then if I understand your question correctly, so we solve it on a grid, and then if too many robots are at the same place, then the other
robot, for example. So in this case, TIJ time for moving point A and G is not deterministic, but it depends on the other robots.
No, it depends on the task, the location of task.
Yes, but in my opinion, it depends on the context also.
So what you mean is, what if the TIJ depend on
if robots have to wait the work of the work of other robots, they have to wait. So we got it.
So the waiting time is already in our formulation. So the task cannot
it's not
start.
a waiting time. You got waiting time for synchronization.
Yes.
Yes, but I talk about the waiting time related to movement in the warehouse.
Waiting time related to movement. You mean so when
if you have to manage the edge capacity,
okay.
Sometimes some robots can go in the same ID, so they have to change the route or wait. So in this case, the time is dependent on the context. Yeah.
So actually, that is one of our extension that I said in future division. When I talk about the multi-agent firefighting, so that is we want to solve it on the grid base. When, for example, if we solve it time step by time step, is that what you mean? But in our current version, we doesn't take that into account.
Thank you. And we can work to Professor Aladio.
Thank you. I have not really any question to ask. Only to say that it was a pleasure for me to exchange with you and to collaborate with you and with your supervisor. And I hope I could bring something and hope you a very good future.
Okay, thank you so much.
Success in all your projects.
It's my pleasure to have a chance to work with you.
Okay, thank you very much. Well said.
Thank you. Maybe you can start with your different supervisor, with Dr. Hanson.
Okay, so good afternoon, everyone. As co-supervisor with Professor with him and Professor Jean-Philippe, I'm very my gratitude to once again I want to say the distinguished the member of the committee. Student to complete his thesis, his work, and once again my honor today to say again, thank again for Professor Nguyễn Việt Hưng and Professor Jean-Philippe give me to opportunity to work with you to help my student Thảo Nguyễn to come to the defense today. Just I'm very happy today. So, and again, thank you very much for all of you.
Thank you. Jean-Philippe? Okay, so it's time to thank everybody. So thank you first to the members of the jury who have accepted to review the thesis of Thảo. Thank you to Viet, who has included me in this co-advisor. Thank you to Anna, who has contributed to this thesis from a research perspective. It was a pleasure to work with Thảo, who is always in good mood. It's a long time trip because this PhD began about 4 years ago. So I think that Thảo has learned a lot during this PhD. He has made progress in writing, talking in English, modeling rigor. So I wish him all the best for his future work.
Thank you. Thank you so much.
Thank you. And the last but not the least.
Thank you, Mr. President. So I would like first to thank all of you for being here, for participating to the committee, and especially the reviewer. And for the context of this thesis is the first thesis in co-tutel between Hanoi University of Science and Technology and Gamorang University. So it's very special for us, and Thảo is coming in as Jean-Philippe said 4 years ago. But he was starting the PhD in Vietnam and for me, and with some problem with the PhD scholarship, so he has not paid during the first year. And so for that, he continued here for 3 years, and so because of this reason that he has done his PhD within 4 years. So thank you, Dr. Tyson, for giving us this opportunity to cooperate with the Hanoi University of Science and Technology. And thank you, Jean-Philippe, for suggesting us this very interesting forum, and for supervising with me. And thank you, Adam, for very many insightful ideas, and always willing to work with us about this problem. And thank you, Thảo, for your work and the sense of practical things. Very enthusiastic about practical application of the work. So it is a strong point. And thank you very much. And I wish you a brilliant future in the professional life.
Thank you.
Bon, vu l'assistance, je ne sais pas s'il y a des docteurs dans la salle qui veulent poser une question. Non. Donc, on va pouvoir délibérer. Okay, ouais. Je vous laisse. Will join me. In fact, it's the time to go to the other room. Let's meet on the other link. Let's say 5 minutes. Okay,
You should to
you have
the
to
other
switch to the other link. See you in
5 minutes. 5 minutes.
You have 5 minutes.
Okay.
Okay, see you.
Can let everything open. Else, can let everything open. We come back in half an hour.
Pour l'instant, elle continue son projet. Oui, mais puis, en fait, tu sais, le problème où c'est pas clair quand tu prends la coupe, et après tu répares les coupes mines et tu répares les arrêts, les arts dans ces coupes mines. Il y a un nombre de réparations qui n'est pas clair. Oui. Si vraiment l'ordre est important ou pas.
Là, ça doit peut-être se voir avant.
Oui.
Théorique, non? Tu me diras si je peux vous aider à quelque chose.
Nó hỏi đấy.
Nghĩa qua đây xong đi à?
Nghĩa qua tặng hoa đấy, tặng bó hoa đấy.
Em mai cũng đi mà.
Đợi tí nhá, anh gọi về phụ anh Phát. Thôi, có vẻ ổn rồi mà. Có bé có xem không? Dạ. Dạ, dạ. Dạ. Cảm ơn mọi người thôi. Chơi đọc không chơi khoảng 15-20 phút rồi công bố kết quả. Dạ. Để thì bảo vệ thì hỏi gì không? Cơ bản. Dạ. Dạ. Dạ, dạ. Dạ. Dạ.
Việt Nam sẽ phải bế tắc.
Dạ, thì chắc thì khoảng 7 phút năm 2 phút công bố này rồi. Dạ, đó ngồi ý. Dạ. Dạ. Các bạn ổn. Dạ, dạ. Được rồi nhá bộ, còn tắt rồi.
Thế thầy có cái thầy vừa nãy mà bảo kết quả anh ấy thì có thể anh nghĩ nên nếu mà trên có thời gian thì trên tên vì anh nhìn kết quả đấy chưa có
cũng đúng.
Thế là thực ra trên bao nhiêu quan trọng mình phải chỉ đổi ra là nó đã hội tụ.
Thời gian nó về thầy report là một tuần trước gì đấy rồi, 2 tuần trước gì đấy.
Trên phần dưới phải có cùng một cái pháp sự bảo một cái khác hơn nhé.
Việt Nam về
Chung kết SEA Games
là nữ à?
nữ. Ngày mai đi thi thì chẳng xem được. Chẳng lắm. Mai có sớm ra xem mai. Thế mọi người hôm nay không ai lên từ một từ đầu.
Không à, mọi người ngồi nghe nói xong mọi người đi. Thì phải câu hỏi gì về mọi người về.
Hai chị, ba chị đúng không?
Ba chị đang có phần.
Thế ba chị bắt đầu cả ba chị đều ngồi lên hết.
Không, ba chị không nghe này.
Em thiệt. Nhưng có mỗi em ngồi đây thôi chứ không. Ba chị không ngồi lên, có nghĩa đến đây một lúc không
Đi đến một lớp rồi.
Còn ba chị thì không cho.
Mấy bạn cũng phòng các thứ. Ba chị không cần để.
Việt Nam thì căng. Trong Philippines đều toàn to thế.
Của đó ấy.
Thường Trung Quốc Philippines. Trông nhiều thịt thế biết
Coi nhá.
thì trận này chung kết thì phụ trách.
Nhưng mà đã coi nhá.
Ra đây chỉ có cặp mấy. Việt Nam mình thì diễn nhanh nhưng mà mình nhiều thịt lắm.
Đây làm một câu giờ 2 phút.
Nhưng mà Việt Nam mình thì diễn nhanh.
Không xem biết mỗi hình như
vừa qua được 5 phút. Như là rồi sao cái gì thế? Đấy thì Sơn là em thấy mãi về sau thì mới vào với sao ạ? Hay là từ đầu? Đấy nhìn màn hình không thấy thầy Sơn. Thế là anh kiểu làm full 100% là làm SD hay là cũng quan gì với khoa?
Đó, thì mình là không xem với khoa. Nhưng mà các bạn bắt là bên này.
Thế anh ở bên đấy bao lâu?
Ở bên đây là mình
Khoa bách khoa.
Khoa về khoa đời có 8 không có định nữa.
Thế thì còn ít hơn Phúc Nguyên một năm về.
Thế là này cũng 1 năm một lần đấy, nhưng mà anh thấy ở bên này cái cụ thể ở bên ở bên này dài hơn.
Thế trong quyển của anh thấy Sơn có tên không?
Có chứ. Đây là đông dân. Chú không thi à? Chú không đấy.
Em có thi. Em xong rồi em vừa về
cái đấy rồi đúng không?
Đây còn được đề thôi chứ. Mấy gì chứ thì
thứ mấy là bao nhiêu nhỉ?
Em có 6 ở đây thứ 7 về, sáng thứ 7.
Thứ 7 là
20.
10 về vậy. 10 là 17.
Em còn phải đi một tiếng sau 20. Còn đến 23 có lại bao nhiêu? Tại vì em có ở Paris đâu, em lên 5 viên luôn. 23 ở Paris. 23 đi xuống Paris.
Thì ba các bạn Paris nói con thứ 2 không?
Thứ 3 Đúng không? 23 đến thứ 3.
Thứ 3 thứ 2 thứ 3.
20 thứ 7. Thứ 3. Có 24 đến thứ 7. Trên cái lên 23 24 trên cái giải phép gần sắp được ôn nhờ CDG khoảng 33 đồng. 33 đồng. Hỏi em à? Rồi, chạy càng quá.
Dạ còn ạ. Không ổn ạ. Không tốt ạ. Dạ không đổi. Dạ thì bảo vệ thì phải. Dạ có mấy bạn người Việt đấy. Dạ có mấy bạn người Việt. Dạ. Dạ cảm ơn. Mình phải khỏe đi ạ. Giờ là 3:30 đúng không ạ? Dạ. Dạ. Dạ cảm ơn. Chú vẫn khỏe chưa? Ở cái Việt nữa. Ở cái Việt. Xem nào. Dạ. Bây giờ lính cười mới đọc cái được. Khỏe được cuối. Một đây là mình đi rồi. Dạ. 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 Dạ cảm ơn.
Nhưng mà cùng người ta cũng suốt là
Bạn em con đấy.
vâng, gì đấy em cũng no rồi ra đấy để cái đấy thôi. Ở đây mấy cái hot này là cái gì đấy anh biết không? Cho hiểu thông gió.
Dạ.
Cái này chắc là thông gió à? Cho hiểu nó làm gì nhỉ?
Sưởi.
Sưởi à?
Nó có sưởi không? Có sưởi không? Không.
Ui, không này thì tại của TV ấy.
Cho bao giờ có lại?
Em vào rồi nhưng không nghĩ nó bị có cả PDA điều khiển của nhà chống đơn tự làm luôn điện thoại.
Được, nó xuống.
Che là gì đấy? Che là nó là gì?
Ghế. Không biết điều khiển được đâu. Đây còn cái này đây, định ghế sao này, đây cái ghế này. Rồi đây là
Che, ghế là ghế này hay là ghế này?
đấy ghế học này. Có phấn nhỉ?
Đâu, cái này là bản đấy mà, bản bút dạng.
Hoặc là cái gì viết lên cũng được.
Cái chì thì thôi thầy Sơn này đứng lên rất là thầy Sơn cũng xếp ra này.
10 năm rồi.
Được rồi đó. 10 năm về đó. Đâu? À, thế thì máy tính.
Màn hình là kết nối với thằng này. Là cái này không quay lại gì được này, mình tôi dưới này.
Tôi cái này làm gì đấy?
Hấp đọc cái cảm kết nối là
Còn thích
cái yêu cầu để mát cái có gì đó
ở đây trên đây.
cái này
Xong rồi mình sẽ ghi tên lên nào đây.
nào
Thế bên này một đồ phải dán tên thì một
tùy phòng, có phòng IT, phòng thiết bị, phòng IT thì chắc là quy hoạch nó nắm chặt hơn. Phòng thiết bị làm nhiều thiết bị nên nó còn không biết.
như này ngon đấy này. Vậy thì ngon rồi. Vậy nó nói sao các thầy vừa đấy không thể nào biết mà sao các thầy của thầy nói rất bé mà một phần trên
cái zoom
không thể nói bé.
Chào mọi người nhá. Đây đang livestream cho mọi người.
Vui tính thế.
Mọi người là xem.
Thế bản premium.
Cái gì premium? YouTube á?
YouTube
YouTube Premium Việt Nam ấy.
Chất đầu tư thế thì nhất rồi.
Chắc anh để xong thì chắc anh nhờ chú setup đồ các thứ. Alo. Dạ em cho chắc phải 50 của đại thì cả tây của đây là. Đó, con bơi trao đấy mà. Con bơi trao mà. Không có câu trả lời được, câu trả lời không. Câu trao thì không phải là phải cắn quả. Nhiều câu có mà. Dạ, kiểu rồi, dạ. Dạ. Em nhớ mấy câu khó thì nhớ, mấy câu trả lời được thì dạ, cái này là có thể câu gì chắc cũng phải dạ dạ còn đây là dạ thì cái này là không cả chắc là phải tắt thôi, phải tắt dạ chắc không được dạ
Anh ra đây xem con gái đi. Livestream anh còn để không? Xong rồi xem cùng.
Ở nhà xem trực tiếp luôn, xem VTV luôn, xem để chúng mình.
Từ đấy làm sao em cái này? Em này giải trí. Con nói hôm nay tôi sẽ thấy mỏng này.
Con đi nào.
Thầy gây không?
Đó.
Em lấy nhiệt tình.
Ở đây học sơ đi không?
Em đang học một
thầy nói hiểu lắm. Cái đấy đủ thì hiểu hết rồi.
hiểu đấy.
Học hỏi người khác là đủ thì
Em học những phần đó, em học rất tốt. Em mà hiểu là rất hiểu.
biết là thế đó. Biết là nó
Vâng, thì cũng mới bảo là điểm thi nổ tất cả các môn cùng lúc.
Sao vậy ạ?
Có Thảo có muốn đưa xem cái cô của em không?
Cho em cô của chúng chậm.
được.
Thôi đừng xem để tí vào thì bất ngờ.
Dạ.
Thế xem bây giờ tí nữa vào bất ngờ hơn.
Có xem cho Thảo không?
Cái tô được te.
Trả tiền cho em đi. Đúng rồi. Trả tiền cho em một tô.
Đó, kéo tay được. Thứ nhất đi Thảo nha.
Ôi.
Ôi. Thảo. Trước giờ chị chưa thấy cô là đẹp này.
Cô của em cũng được đẹp như này luôn.
Cô bé này đó, cô bé Tú Lam. Đây đây.
Không đẹp một quên.
Ok được.
Quên để chị không là em vừa về.
Được.
Em đến 2 giờ.
Xong rồi.
Lúc ấy thu em. Ngồi được 3 giờ.
Thế em làm nóng.
Em nóng lắm. Ngon. Sao chú hỏi sao nào ổn không? Bọn em ngồi xem đấy. Bọn em ngồi xem là chị bày chú. Cái này còn chạy không? Cái này chạy không?
Đó, chạy đó. Cả nhà thì cũng xem đấy. Hò hai công tụ vào đi. Lại xem.
Đã thấy nhiều comment phết, không thấy đâu.
Ô, cô hỏi comment nữa.
Em chưa là gì?
Chờ xem kết quả.
Thế nào? Đến cái đoạn mà caption là bắt đầu nghe rồi không? Bạn trước nghe
Hỏi cái thẳng không? Chiêu rồi không? Nó là xịt con này.
Thầy đi ra provide một good presentation. Rồi là đầu tiên được thầy sự good rồi đó.
Hôm qua cả còn chích. Thầy bảo là cũng được, chứ thầy không bảo là được.
Tạo ổn.
Cũng tạo ổn đâu. Mình nghĩ là ổn. Kiểu lần đầu tiên chị thấy thầy kiểu chị thấy Thảo kiểu gọi là gì đó, suy nghĩ về từng câu chữ của thầy.
Ôi thì đúng là để
nhưng mà em buồn cười
thế nào mà
em buồn cười cái quả
mọi người như Thảo còn suy nghĩ về từng câu chữ của thầy đúng không? Kiểu chị em mình nó còn đỡ lạ chứ.
Chị buồn cười
đầu tiên luôn.
Chị buồn cười cái quả nửa đêm hôm qua, cái người mà mai trình bày thì xuống trên thì còn cái người trên thì bên sửa sai. Đầu bếp này hơi bị đa năng. Chị Tiểu Tiên.
Chị xem như nào em trước em chưa bao giờ em cùng em không mời em.
Sao em muốn gửi cả lên group anh chị em cái livestream này. Biết của ai vào xem.
Thì như thế này xong rồi mình
Thế là nước hoa tóc à?
phải nước hoa dưỡng với lại để cho
nó áp bớt cái mùi nem thì mùi gì?
em cảm giác mình toàn mùi thịt nướng ấy.
Em với chị An là mùi thịt nướng, chị là mùi nem.
Em vừa em thử cái đấy em xem nó là được.
Còn pin không? Máy còn pin. Giai đoạn đầu phải chú hơi run. Em không biết là muộn. Em không biết là muộn. Thế thì đến 2:15 rồi em sẽ xuống trường này. Cái đầu ngoài nó bị ngáo đó.
Mày có đang cà phê quỳ
15 phút rồi à? Không phải 3 giờ hơn mấy. Các thầy đi từ xin ra nó giống như ở trong bao giờ em sao?
Nhưng bây giờ là phải có cái lược để mình trái xong thì nó giống như có quảng cáo
thì như vậy cái xa đấy không có một cái nào phải có một cô.
Cố hai mày cố á, hai cô.
Em gặp cô Fatiha cũng em đi lấy
sai
nhưng mà cô cà phê
có bỏ để đây mà trong cái tóc chị nó có để sữa rồi hơn thì vẫn trong hơi hơn
chị bị ảo tưởng sức mạnh.
Tại vì cái này là nó làm nó có một lần nữa rồi không phải thơm. Em sau khi xem nãy em không xem được xem lại nghe
mình lại nhớ đến hình ảnh ngày xưa mình bảo vệ
thế này
con nó bé hơn chị bảo vệ ăn thịt hoa
Phòng là đẹp mà.
đây là cái phòng đầu tiên mà em gọi là gì cái lúc mà nói gì bốc ấy là cái phòng này là ở bên phòng kia gì bốc hộ cũng nói bên phòng này đúng không?
Gì bốc phòng nào nhỉ? Hình như
phòng này ở phòng bên kia phòng ông nhưng mà nó y hệt như này hai ông kia này như nhau
còn to hơn chứ nhỉ?
Đúng rồi bằng nhau hết rồi. Hôm qua bạn không thấy bọn em đến khoai không đến bọn em đến 7 người này.
Không nhưng mà nó giống như kiểu là mình ngại trình bày trước mặt người quen kiểu chị mà bây giờ mà bắt chị nói tiếng Anh trước mặt mọi người chị cũng bị ngại.
Trước em bị ngại lắm ấy vì vậy em mất ngại
nhưng mà nói tiếng khác thì ok rồi chú ạ tí nữa chú phải tháo đôi giày này ra để em trao tặng quả hôn.
Thảo là lúc nãy tớ hỏi Thảo là giày mới thử đấy cậu nhớ không? Đây là cái thấy cậu đi cái đôi giày này ấy rồi cái lúc mà cậu nhớ lúc xưa nãy trước khi ăn cậu vào phòng tớ với ông Liêm đấy lúc tớ cũng bắt đầu hỏi xem đến
chú tháo ra nhất để em một cái phải trao em cho có gì để trao
đi làm chân đất gì
chú đi làm chân đất thì không em về cái
nhau người bao nào
cho em tặng chú cả bữa cơm một bữa tiệc một bữa tiệc với bạn
đây quà này quà tặng kèm với Thảo nhất đấy được lắm quà nữa sang quà cơ bản chỉ ủng hộ thôi đúng
để lắm chị mới hộ
cái zip tóc
cái thế
số phận cái mắt năm ở đây đã
chặt nhậu đã
rồi thế rồi
cái ngủ chơi đi
thật đấy rất buồn
nhưng mà chị thấy chúng ta là các kiểu năm nhất là đẹp xong rồi năm hai là rất xấu xong rồi năm ba đến bọn này là đẹp trở lại thật thế
gặp về là
em nó rất xấu
lúc mà đã
năm hai
để tận bài nó
lúc
về
nào sang đến lúc em nghĩ em chị đã nhưng mà chị kéo lại sự đã sớm hơn em
phải đội ơn hùng đi
hùng nghe nói sau này hùng cũng đang bị post đó
thế là hùng có học Paris chị tưởng nó Việt Nam
em thấy bảo hùng có học người Việt Nam
mọi người đến thế là đến ăn cơm thế
xong chưa?
xong rồi cô được rồi
đang chờ đúng không?
để kết quả rồi
Đó, đến vào giây phút này thôi.
đúng rồi
nói chung là em biết cái bảo vệ quan trọng nhất là lúc nào không lúc này và lúc ăn cô
Rồi, được rồi.
Cần có sự hiện diện của mọi người. À chị ai
này cái livestream thì hợp lý đấy nhỉ?
Nhưng mà YouTube này phải mua đúng không anh? Mua premium.
Chị có premium.
Đấy.
Đấy là premium và livestream rồi bạn.
Không thì đang có sốt.
Không biết là nền tảng có cái hơn. Nó comment được như này.
Chưa.
Quả cắt.
Mình cho mượn bó hoa này.
Bó hoa để thử nghĩ đã.
em không biết đâu rồi, biết đâu rồi. Thảo thẳng biết đâu rồi.
Về ổn đi rồi.
Về
Chắc hoa cái về luôn.
Chắc có cái mày của mình của máu có đâu đây xem cả.
Không hiểu nghĩa đây. Thi thì không có thi đấy có gì đâu.
Mai thi
Thì thế mai thi thôi. Con anh cứ ngồi đây.
các anh em
Thì thật đó chứ.
Không em lên đây em không thể tưởng không vợ nào.
chị đi chị quay về mà. Đi có mấy ngày thôi.
Để đấy.
Nhưng mà cứ tắt đi cho nó chắc.
Em coi, em bao nhiêu người xem? Coi không phải tắt đâu.
Phải tắt.
Phải tắt đâu em ạ, em phải bật. Vậy chị không biết tắt ở đâu? Bởi vì chị không biết dùng cái đấy.
Livestream YouTube còn nét hơn livestream ở Facebook.
Ôi nét lắm nhá.
Có 3 người.
Chắc là bố mẹ đấy.
Bố mẹ với anh. Một nữa.
Nét lắm rồi đấy, bọn mình xem nét được.
Livestream
Phải có phòng phải bạn này đúng không? Đúng không?
Bọn em xem nét.
Đúng rồi, nhìn nét khác. Còn zoom các thứ lên
Nhưng mà mỗi tôi không nhìn được slide số mấy.
Nhưng mà zoom thế là ấy rồi chị. Thế
nhưng
là
mà
ấy rồi.
cái trên phòng mình soi.
Gì cơ?
Ý là không nhìn thấy slide số bao nhiêu ấy.
Phòng này ngon mà. Phòng đẹp.
Quan trọng bây giờ quay được cái phòng thế này.
Tắt bút để đi cho đỡ chói.
Bật cái spotlight kìa.
À cái hôm mà cùng hôm em bỏ về cùng bây giờ rồi đi.
Voilà, nous allons.
On se met où? L'espace est là, et puis vous allez essayer de après bon.
Tu peux mettre les autres membres.
Je vais admettre tout le monde comme ça.
On va mettre sur l'ordinateur.
Ils sont là? Non. Il faut que je le re-admette.
Ah, ils sont dans la salle d'attente.
Oui.
Non, j'en ai pas.
Il manque encore quelqu'un? Seul, non?
Ah si, vous êtes ça.
Il y a seul encore. Ah si, attends.
Comment on a dit en français qu'on se retrouvait?
Ah, oui.
Ah bah voilà. Comme ça.
L'étoile.
Ça vous fait tous. Non, on ne te voit pas.
On te voit pas.
Décale-toi un peu par là.
On te voit beaucoup.
Oui, voilà.
Parfait.
Bien. Monsieur Chitao Nguyen, vous allez présenter votre travail de recherche de doctorat avec beaucoup d'aisance et de pédagogie. À travers votre présentation, qui a été jugée bien construite et très claire, le jury a apprécié l'intérêt et les perspectives importantes de ce travail de recherche. Vous avez démontré l'originalité du problème étudié et les nombreuses perspectives d'application dans le domaine du transport et de la logistique. Vous avez démontré par votre travail un large spectre de compétences qui sont liées à la modélisation mathématique, aux méthodes d'optimisation exactes et approchées, et à la mise en œuvre d'algorithmes. Vous avez su vous inspirer de la réalité du terrain en vous intéressant à l'utilisation des robots coopératifs dans des entrepôts logistiques. Et on a noté ici qu'il y a eu des discussions avec le jury qui a porté sur une grande variété de questions, tant sur les aspects théoriques qu'applicatifs. Pour toutes ces raisons, le jury, à l'unanimité, vous décerne le grade de docteur de l'Université Clermont-Auvergne dans la spécialité informatique.
Merci beaucoup.
Félicitations. Alors, vous avez un serment à faire. Vous avez le texte. Vous avez le texte pour le serment. C'est dedans. C'est petit.
Il y a deux versions en anglais et français. In two versions, English and French, so you can choose one of them. Here is English, it's French.
Ok, j'essaie de parler en français. En présent de mes pairs, parvenu à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête du savoir, l'exercice d'une recherche scientifique exigeant en cultivant la rigueur intellectuelle, la réflexibilité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intégrée dans mon rapport au savoir, mes méthodes et mes résultats. Oui. So I would like to thank, first I would like to thank Viet and Philip and Aitata have been very patient with me in this journey. I would like to thank all the jury members for being here today and on the video. I would like to also thank my friends in DeVos community also. And I would also like to thank my family. They are watching live from Vietnam. Con cảm ơn bố mẹ. And last but not least, my girlfriend.
Restez un peu pour une photo et puis.
Pour les photos, ça marche.
Ouais, ok. Et puis on.
Pour le pot, ça sera un peu difficile, mais pour la photo,
Nous, ça va être là.
Mm-hmm.
je vais me mettre à côté.
C'est le président. C'est le président.
Ah, bah, vous pouvez pas être en caméra.
C'est bien que.
C'est pas vrai.
Bon.
Oui. Ok, c'est très beau.
Ok, une photo déjà.
Merci beaucoup.
After this, we have a poll.
Congratulations.
Thank you. Thank you. After this, we have okay. Thank you.
Merci beaucoup.
Merci.
Tous les autres membres. Nous, on va profiter du pot, mais malheureusement pour vous.
So we have a photo there as room A.
Vous pouvez venir, hein, c'est vraiment
Ça marche, on arrive.
Allez, c'est parti. Merci.
Merci.
Merci beaucoup. Merci encore.
And again, thank you very much.
Thank you. Congrats. And good luck for the future.
Thank you. Merci Sonia. Merci.
Bye.
Merci.
Bye. Bye everyone. Thank you.